Hi, it's Mr. Baker here, and today we're going to be looking at the conservation of momentum. Okay, so today we're going to be looking at the conservation of momentum, and if you can see this image, this little clip, we're going to try and explain why does a snooker ball do this. Okay, so have a look at this animation. You can see where it's from. It's from this website here, myphysicslab.com, and it shows something called a Newton's cradle. And what a Newton's cradle is are some spheres, kind of like ball bearings, but like quite big ones, on a line. And you can see that when one ball hits from one side, the only other ball that comes off is another ball from the other side. This is a brilliant example of the conservation of momentum. Now, if you can remember back to last lesson, we said that momentum was the mass times the velocity. It's about things being difficult or easy to get moving, and how difficult they are to get them to be stopped. So if you've got one ball of a certain mass and a certain velocity hitting into a bunch of spheres like this here, then what happens is that at the end comes off exactly the same mass with exactly the same velocity. And that's what the conservation of momentum says. The conservation of momentum says that the momentum before a collision equals the momentum after a collision. So when one of these spheres hits into a bunch of spheres, it crashes in with a certain amount of momentum. And so what's got to come off that, what's got to have happen afterwards, is that that momentum has got to be conserved. And so one ball hits in with a certain mass and velocity, so one ball must come off. It's got the same mass, and so it's got to come off with the same velocity. Okay, so the conservation of momentum can be described like this. The sum of the momentum before a collision or an explosion equals the sum of the momentum after the collision or an explosion. So momentum, remember, is mass times velocity. So the mass times the velocity before a collision or an explosion. And we're talking about the total amount. So if you've got more than one thing moving, you've got to look at both their masses, and you've got to add up the momentum of both of those objects. That will equal the momentum of both of those after the collision. Okay, so that's our definition, and I'm going to show you some examples which hopefully will make it a little bit clearer. Okay, so what is the conservation of momentum then? So if two objects collide or interact, the forces acting on each one will be the same size but in opposite directions. The same is true for the change momentum of each object. This means that the momentum lost by one of the objects will be gained by the other object. Therefore, when two objects collide or interact, momentum is conserved. Okay, so let me show you this example. This is an animation again from the FET website. It's their collisions lab, and you can see I've got two balls here. These two balls are the same mass. You can see down the bottom that the red one is 1.5 kilograms and the green one is 1.5 kilograms. So I'm going to start the red one moving, and we'll see what happens. Okay, so did you see what that happened? So the red one moved along with a certain velocity, hit into the green one, and the green one moved off with the same velocity. Let's look at that again. So the red one goes off, hits into the green one, and the green one moves off with that same velocity. Now, the momentum of the red ball we could work out by calculating the mass times the velocity, and we know that the conservation of momentum says that the momentum before the collision equals the momentum afterwards. So if that red one stops, then the momentum of the green one has got to equal the momentum of the red one. And because they're both the same mass, then that means that the velocity of the green one equals the velocity of the red one beforehand. Now, there are two types of collisions that we can have. We can either have collisions which we call inelastic, ones where the kinetic energy after isn't the same as the kinetic energy before. And this is what most collisions in real life are like. Or you can have elastic collisions, and elastic collisions are ones where the kinetic energy is conserved. So the kinetic energy before the collision equals the kinetic energy after. So we've just seen an example of an elastic collision. Let me just show you an example of an inelastic collision. And can you see what happens? Okay, so in an inelastic collision, the kinetic energy isn't conserved. Now, kinetic energy is to do with the mass and the velocity, isn't it? So if you can remember the equation for kinetic energy, it's half times mass times velocity squared. But we know that the momentum is conserved. So basically, in inelastic collisions, the objects normally stick together, or they crumple, or something like that. So here, if you can see what happens, the red one goes off with a certain velocity. And what's the velocity of both of them together afterwards? Well, it's about half. And the reason it is exactly half. The reason it's half is because if we've doubled the mass of this combined object afterwards, then we've got to half the velocity of them coming off, because we know that the momentum before equals the momentum after. And let me show you this other example here. So we've got our two balls here, but they're going to go in opposite directions. They've got the same mass, remember. So when they hit into each other now, because they've got the same mass and they have the same velocity but in opposite directions, then when they hit into each other, they completely stop, because the momentum was going in opposite directions. Remember, momentum is a vector, and so the sum of the momentum before is going to be the mass times the velocity of this one plus the mass times the velocity of this one. But the velocity of this one is negative. So if the velocity here is 1, but minus 1, and the velocity here is plus 1, then we've got 1 times 1.5, which would equal 1.5. And here we've got 1 times 1.5, but it's minus, so it'd be minus 1.5. So the sum of both of those, we've got 1.5 minus 1.5. The sum of those momentums before is actually 0. So that means that the sum of the momentum after has also got to be 0. In other words, these objects, because they've both got mass by itself doesn't have a momentum unless it's moving. And so the mass of both of those times 0 velocity would equal momentum as 0. Right, so let me show you an example calculation of this. So if we've got in physics, we use these trolleys a lot to crash things into. So two trolleys collide and stick together, so we know it's an inelastic collision. From the data below, calculate the velocity of the trolleys after the collision. Okay, so we know that trolley A has got a mass of 3 kilograms and it's got a velocity of 8 meters per second before the collision. So we know that the momentum of that is 24 kilogram meters per second. Trolley B has got a mass of 5 kilograms and before the collision its velocity is minus 4 meters per second. So it's got a momentum of minus 20 kilogram meters per second. Okay, so we've worked out the momentum of both of those individually. So the total momentum before the collision, we literally just add those two together. So the conservation of momentum says the sum of the momentum before the collision equals the sum of the momentum after. So the sum of the momentum before the collision is going to be 24 minus 20. So it's going to be 4 kilogram meters per second. So that's got to equal the momentum after the collision. The mass after the collision is going to be both of those stuck together, because that's what it says in the question. The two trolleys collide and stick together. So the total mass is going to be of both of them together. The mass of that is 3 plus the mass of that is 5. So the mass after the collision is 8. We want to find the velocity after the collision. So we know the momentum after the collision, and we know the mass after the collision, and we know that momentum equals mass times velocity. So that means that the velocity after the collision equals the momentum divided by the mass, which equals 0.5 meters per second. Okay, so these are some of the trickier calculations you'll have to do in the GCSE, so it's worth having quite a bit of practice doing these ones. But that's pretty much this lesson over. So this is what you should be able to do today. You should be able to state what is meant by momentum, describe what the law of conservation of momentum says, and be able to calculate the velocities of objects after impacts and apply the principle of conservation of momentum to a range of calculations involving the velocities of objects. And so back to our initial question, why does a snooker ball do this? So why does it stop after it's smacked into another snooker ball? Well, snooker balls have got the same mass. So if you smack a snooker ball into another snooker ball at exactly the right angle, so literally straight on, then because of the conservation of momentum, the momentum before equals the momentum after, and so the momentum of the white snooker ball will just get passed on to the momentum of the black snooker ball, and that's why that will do that. So I've been Mr. Baker, this has been the conservation of momentum, and I will see you next time.